Hello everyone. Today's session is about how workloads running on mainframe technology such as IBM Z, Unisys ClearPath can be migrated to AWS Cloud using the refactoring approach. We will focus on automated refactoring in particular. I am Madhuri Susarla, working as a senior solutions architect in the partner organization of Amazon Web Services. With me is Kirti Shah, who also is a senior solutions architect in the global financial services. At the end of this webinar, you will be able to understand how to convert your mainframe code into a modern technology and deploy on cloud. This is also called digitalization of code. We will also try and have some time left for Q&A. So what are the key mainframe modernization drivers? The first and foremost is cost. Mainframes can be very expensive. They cost several thousands of dollars per MIPS. So customers want to reduce their mainframe cost by reducing MIPS consumption and thereby shrinking ISV license costs. They favor the pay-as-you-go model. We have seen customers reducing the cost between 60% to 90% once they migrated to AWS. Agility. This is the second most important reason, and customers have difficulty deploying new business functions with their mainframes. They want to reduce the time to market. They want to move away from large monoliths. They would like to adopt CI/CD practices, microservices, and really benefit from cloud speed. From a technical debt perspective, we see customers willing to suppress legacy proprietary platforms and avoid vendor lock-in. Mainframe modernization also supports digital strategy, and it will fill the mainframe skills shortage. Many customers have challenges finding the people with the right expertise to maintain their mainframe because a lot of mainframe specialists have either retired or will retire soon. So customers want to solve the retirement skill gap and attract new talents with cutting edge skills. This also helps with data analytics because mainframes typically house large volumes of business critical data across the decades that they have been running through. These are the most common reasons why our customers modernize mainframes with AWS. So what are the different mainframe modernization patterns? Based on our experience across several customers, we have arrived at two families of patterns. One is short-term migration and the other is augmentation. Short-term migration is about shutting down the mainframe in 1 to 2 years of time frame. Shorter duration minimizes the risks and provides a faster ROI. In case of augmentation, the mainframe is kept and the benefit from AWS value proposition is obtained in parallel. Within short-term migration, we have different types of migration. One is hardware emulation, where software stack is entirely moved. An example of this is where dev and test environments are offloaded to AWS. The second one is middleware emulation. In this case, code is ported and recompiled into a middleware emulator. Basically, this helps in migrating away from proprietary and expensive mainframe hardware as well as software. The third is automated refactoring. In this case, code and data are automatically converted using third-party tools and refactored to a cloud-native stack. For example, migrating away from languages such as COBOL, PL1 and Natural to something like Java or Amazon Aurora. The fourth approach is basically modern middleware replatforming. In this case, applications and data are migrated to a similar modern middleware on AWS. An example of this is where there is a workload running on IBM WebSphere application server as well as IBM DB2 using Java, PHP or Perl workloads. In case of augmentation pattern, There are different types of approaches, such as data analytics, where AWS is used to perform analytics on the data that is housed on mainframe. So the mainframe is kept while analytics are performed on the mainframe data using AWS. The other approach is where AWS is used for new channels, such as mobile or voice. The third approach is using AWS for dev test environments. So rather than adding more to their mainframes, customers offload and scale dev test environments on AWS. The fourth approach is where AWS is used for purely backup and archival. Now let's go a little more deeper into each of these patterns. You can see here the short-term migration options in one slide. On the left-hand side, you can see the mainframe platform with different subsystems such as physical hardware, operating system, the middleware, applications, and data. On the right-hand side, you can see the various migration options and how components are changed for each option. In blue, what stays the same, and in yellow, what changes. That's how the color coding goes. So in case of the legacy hardware emulation option, the very first option, the hardware emulator replaces the mainframe hardware. Mainframe operating system and applications stay the same. So you can see in blue that all the mainframe software from the operating system and upwards stays the same. This is really a lift and shift approach. In case of the second option, which is a legacy middleware emulation option, the middleware emulator replaces mainframe middleware APIs only, and operating system APIs required by the application. This is the porting of the application where much of the application source code is recompiled without changes. But for the change dependencies, there are some necessary adaptations. So you can see in yellow where the middleware emulator fits. You also see that there are some code adaptations that are required. In case of the third option, which is legacy automated refactoring option, code, data, and dependencies are automatically converted to a modern language. The data is converted to a modern data store, as well as any frameworks that are used will be converted as well. So this guarantees functional equivalence, and you can see in blue that the business functions actually stay the same, but the entire software stack in yellow is changed using modern technology. We will dive deep into this very approach the rest of the session. The fourth approach is where we're talking about modern middleware replatforming approach. This applies only to modern languages such as Java, PHP, and relational databases that are right now running on mainframe, but they're also available on x86 systems as well. So in this approach, basically you can reuse application code as well as databases. And you can also see that the operating system change is mostly abstracted by the middleware. So looking at all of these options, the two most popular approaches with our customers are the number 2 and number 3, which are middleware emulation and automated refactoring. So here we have vendors that have partnered with us and offer sophisticated tools under each approach. For example, Blue Age, TSRA, Heirloom Computing, and Modern Systems have pertinent solutions in the automated refactoring technology. Also given in the slide are players with solutions as well as tools in other approaches that we have talked about, such as middleware emulation, where Micro Focus is one of the players, and Attunity in the augmentation pattern. Okay, so let's take a closer look at automated refactoring approach. So what we've learned so far is each migration option has its preferred use cases and unique value propositions. So what we are trying to do here is basically compare the different approaches using the key characteristics such as project cost, project duration, and cloud agility. If you look at the duration, hardware emulation is the fastest because the impact that it has on code is the smallest. In fact, it is nil. So it can be done in a matter of days or weeks. Middleware emulation and automated refactoring, both of them roughly take about 1 to 2 years for a average size workload with a few million lines of code. Another option is basically repurchasing, which we've not really talked a lot about because it just means that we are purchasing a new software and customizing it. So this is likely to take longer than automated refactoring or middleware emulation or even hardware emulation because of the customizations required to suit the business requirements. The longest is manual rewrite because of the new specifications, new code, and new tests that have to be developed. Now let's look at the cloud agility. And when we mean cloud agility, it's about how this approach promotes the use of AWS managed services, how it enables using microservices and CI/CD practices as well. So hardware emulation is still using the mainframe operating system on AWS. So it really cannot benefit from AWS managed services. If you take the middleware emulation, it can use some managed services such as RDS for database and can also introduce a CI/CD pipeline for application agility, but in a very limited way. Automated refactoring takes this one level higher because it promotes a service-oriented, elastic application. It will also enable using CI/CD practices more deeply and creating a cloud-native application. But manual rewrite is the one which gives you the highest amount of agility because you can pick and choose from the AWS services that you are interested in. So it looks like manual rewrite is the best option for maximum cloud benefits. But there is a catch here because large mainframe manual rewrite projects typically have higher risks associated with them because of which they are more likely to fail. According to a study by the Standish Group, only 6% success rate is seen for projects over $10 million of budget. The reason for this is because business rules and logic have to be extracted from undocumented code manually, and therefore functional equivalence cannot be easily established. So risk is more manageable when the scope and teams are smaller. I've also given some case studies where this is indeed the case. The scope is very large, the budgets are high, but the projects failed because of not being able to meet the deadlines. So how do we de-risk a large mainframe migration to AWS? It is by following the principles of AWS mass migration methodology. Basically, start small, automate as much as possible, migrate quickly, and then optimize. So all of this is possible if we adopt automated refactoring approach. And the way we can summarize automated refactoring is basically it will help in eliminating legacy technologies. It will help in getting rid of technical debt because we no longer have to stick to a certain technology or certain hardware. This in turn helps in cost reduction. It will help shrink ISP license costs, leverage pay-as-you-go model, increases agility because we are now able to adopt CI/CD practices, become a cloud native application, and we can even adopt microservices. And this also promotes hardware agility because moving to cloud means you can enable high availability for your workload. You can provide highly scalable solution and make your workload elastic to the load that the workload experiences dynamically. And it will obviously avoid the hardware failures because the resiliency is built into the AWS Cloud platform. Another important callout is the functional equivalence that automated refactoring guarantees. As the code is generated automatically and the user interfaces are kept like to like, there is no need to retrain end users. And we will see how this works in the demo that follows. And there is also no manual engineering efforts required in this approach other than testing. So ultimately, this reduces overall costs. On the left is what you have, a mainframe with COBOL, PL1, assembler, JCL components, as well as other components such as transaction manager, batch, subsystem, database, data files, and so on. So on the right is AWS Cloud. So what we have in the middle doing the conversion is the automated refactoring tool. For example, this tool converts the COBOL PL1 natural code to Java or .NET languages that can be deployed on AWS Cloud. So as you can see, the refactoring tool is very central to this approach. And because the process is mostly automated, the development speed is increased and risks are reduced because of the functional equivalence brought in by the automation. So the diagram on the right actually shows a sample deployment on Amazon EC2 instances for compute, Amazon Aurora or Amazon RDS for data store, and a number of other services as well. And we will see more of this in the subsequent slides. So what are the exact detailed steps or phases in a typical automated refactoring migration to AWS? To begin with, you need to identify the workload. And one of the best practices is to do a complex POC that has a representation of all the complex test cases within the workload. The complex POC need not be largely scoped. And depending on the mainframe that the customer has, the complexity can reside either in batch or in online or the latency requirements or the throughput requirements. So tool evaluation is very important to suit the requirements of that particular workload. So once this is done, the next step is to feed the source code to the tool. Many refactoring tools have built-in features to analyze the legacy code in various ways, such as total lines of code, the inventory list, the dependencies among the different code components, etc. And once the code is baseline for the POC, the analysis can be run to obtain something called an application object model. This is usually a technology neutral model such as an UML model or a model driven architecture kind of a model. At this point, you will have to choose the target stack that is of your interest, such as a Java stack or a .NET stack, or there could be other options as well. And once that is done, the code generator generates the code for you, which can then be deployed onto different AWS services, such as Amazon EC2, Amazon ECS, Amazon RDS, etc. We will see the detailed target architecture in the subsequent slides as well. A common question is if the generated code quality meets the standards. And this can be ascertained by running the code quality checker tools such as SonarQube or PMD. And once the quality is established, code is unit tested, and then it is ready to be hosted on AWS. An important call out is that the automated refactoring approach guarantees functional equivalence, and we've seen that. But we still need to do testing to validate that. So at this point, the POC is complete, and once everything is satisfactory, we should size the actual project and break it down into work packages in order to do iterative development. And the code analyzers will come handy to do that as well, because they will be able to produce process control flows, which will help you to do the packaging into different work packages. So here we take a closer look at the code analysis tools. Actually, these are more of reverse engineering tools for deep dive analysis of legacy. They can provide graphical views of in-depth code analysis such as different assets and their LOCs, dependencies such as copybooks, missing copybooks, and other dead code or even calling trees. For example, in this illustration, you can see the relationships between CICS maps, which are the purple dots, the VSAM files, which are in red, and the corresponding COBOL programs, which are in orange. So all of this will help you isolate applications and come up with work packages for iterative development. At the end of this, most tools generate a technology agnostic application object model. Some tools also have an online simulator, which will help you enable budget calculations for estimation purposes. The next step is to digitalize the code. Some automated refactoring tools are sophisticated enough to transform the complete legacy stack, including code, data access, data stores, any frameworks that are used, transaction subsystems, and so on. And some can do it with zero manual coding as well. And most of the mainframe programming languages are supported by the automated refactoring tools, including assembler. Data stores such as VSAM files, the DB2, and flat files are converted into modern databases such as Amazon Aurora or Amazon RDS. So here I have given a snapshot of the generated code. As you can see, this is object-oriented while being able to handle the nuances of COBOL such as low values. We will also be able to spend more time going through the code during the demo part of this session. So who are some of the customers that are actually in production today that have used the automated refactoring approach? The US Air Force is one such customer. They have deployed their supply chain and equipment support workload on AWS using the automated refactoring approach. They have the annual operating costs of over $30 million with 3 million lines of COBOL code, 10,000 lines of C code, and a DMS network database. The solution was to use automated refactoring from COBOL and C to Java on AWS. The target stack includes Amazon RDS, Amazon EC2 with autoscaling groups, and elastic load balancing. The benefits were in terms of cost savings of over $25 million per year, infrastructure agility, elasticity, and choice of AWS services. The other customer is New York Times. New York Times needed to reduce operating costs and enable technical convergence with other platforms. The New York Times automatically refactored their ZOS-based CICS applications to Java. With this migration, the New York Times achieved 70% operational cost reduction, accelerated software development, and cloud native services adoption on AWS. So, how does a typical modernized legacy architecture look like on AWS? Let's see this for both batch and online applications. What is shown here is more like a reference architecture and not necessarily a direct tool output. But some of the tools have packaged rules where you can specify the AWS services that you are interested in. So given here is a highly available architecture for an online application that had been automatically refactored. As this refactored code already uses modern NTO enabling frameworks, it becomes easy to deploy the code into layers such as front end, API layer, application layer, and database layer. The front end layer uses Angular, HTML. For example, API layer is comprised of Amazon API Gateway and containerized services that use Spring Boot. Data layer is on a cloud native database such as Amazon Aurora. As you can see, at every layer, it uses a multi-AZ architecture enabling high availability and ruling out any single point of failure. On the right is a DevOps pipeline that is automatically created by some tools. If not, it is also easy to create the DevOps pipeline on AWS on your own. This architecture also incorporates observability in the form of Amazon CloudWatch as well as AWS CloudTrail. And all of this is just configurational without much coding efforts. Now let's look at the batch architecture closely. Again, this may not be a direct output of the tool itself. So there are three aspects to mainframe batch migration. The first one being the batch logic that is encapsulated within the jobs or the JCLs. Automated refactoring tools encapsulate this in the batch layer comprising of frameworks such as Spring Batch and Groovy. Spring Boot is also used for generating the services. Here, each former batch program typically becomes a Spring Boot autonomous executable. Or it can even be a Groovy script. In the ideal state, they should be further broken down into business services that are reusable with the online components as well. Next, the batch execution runtime environment with the job management input, outputs, and the utilities such as IEBgener, IDCAM, sort, etc. So how do we convert this into code that can be run on AWS? Again, all of that is encapsulated in the batch layer by the refactoring tools and deployed either on Amazon EC2 or as Amazon ECS tasks. The last thing is the batch scheduling. Batch scheduler typically coordinates the batch jobs. It also takes care of restart and recovery. This can be visualized as schedulers such as CS7, Control M, and it also depends on the complexity of the batch logic. These schedulers are run on EC2. The other option is to use AWS Batch, which is a fully managed service that has batch management capabilities. For example, there could be simplistic scenarios such as long-term data storage job. This is typically the GDG file step in a JCL, and that can be easily converted to a single Lambda function leveraging lower cost storage such as Amazon S3 and Amazon Glacier, and AWS Batch can be the scheduler as well. So now I would request Kirti to show us a demo of what we have discussed so far.
Thanks, Madhuri. For the purpose of this demo, we have built a small sample application in Mainframe that we will be refactoring into Java. Now I have logged into CICS here. Let's look at the sample order application. I press enter. Now in order to display my customer information, I press enter, give my customer number. And here you can see the name and address of the customer is displayed. Now we will look at how we can migrate this application to AWS by refactoring the code. Now, in order to do that, I'm going to my console here. Now I click on databases. What I have done is I have created an Aurora Postgres database, which I would like to serve as our backend. Now I chose Aurora Postgres as Amazon Aurora combines the performance and availability of high-end commercial databases with the simplicity and cost effectiveness of open source databases. Now it also provides 3 times better performance than typical Postgres database. So I'm using this to serve as our backend. Now I will also like to show you the EC2 machine, which I have already spinned up. So let's go to EC2, instances. And here, this is my EC2 machine, which I have spinned up. Now let's RDP into this machine. So here I have RDP into my machine. Now in this machine, I have already uploaded some of the tools from our partner Blue Age, as well as I have uploaded my sample application code, which I will be using for our demo today. So the first tool which we will be using is Blue Age Analyzer. Let's go ahead and open up the Analyzer tool. Now the Analyzer tool creates a platform independent model of the application. Let's give Analyzer tool a workspace that we'll be working on. Let's import our legacy assets. I'm giving my project name as test refactor. Press next. Now we go to the location of where our code is. Workshop, Murak. And now here you can see we have all our BMS maps, CICS, COBOL, copybooks, JCL, etc. I select this and then press OK. I click on next. Give my database a name. This is an internal database which will be used by the tool. Click on next. Select this and then press finish. So here it is importing all our code. And now here you can see that there are multiple graphs that has been generated. Now this tool produces in-depth legacy code analysis, and customer use it for application inventory, dependency analysis, and much more. Now let's look at one of the graphs. So you can see that you can use these graphs for the dependency analysis. For the purpose of this demo, we are not going into details. What I would also like to show you is all the pre-process file which an analyzer has created. For that, let's go to navigations, test refactor, documentation, and then gap walk. Here you can see that all our COBOL code has now been broken down into 2 parts. One is data structure, another is statements. Also, I would like to show you our JCL, which has now been converted into a Groovy script. Let's go to script, Murak, JCL. Here you can see that our JCL has been changed into Groovy, and this is going to behave similarly how our JCL used to behave. We also have some JSON files under the list cat. This is going to be used later on when we are going to define a schema for our Postgres database. And here is all our CICS code, which has been now transferred transformed into the preprocess file. Now, in order to go to the second step, which is doing the refactoring of the code to Java, what we will do is let's go ahead and export all the generated code. So for that, I go to Assets, Export DSLs, and then press OK. So it has now exported all my generated code into a local Git repository. I just say continue and then press OK. Now let's go ahead and open up our second tool, which is Velocity. So here I have opened up the Velocity tool. Now let's just import the application object model that Analyzer created. For doing that, let's just click on Import, go to General, Existing project into Workspace, press Next, browse the location where we have all our Git code. So in order to do that, I'm going to my Git folder, click on Test Refactor, and then just press OK and then finish. So now we have got all our legacy code here. Now, in order to do the transformation, we need to create a new Blue Edge project. Let's give our project a name. Click on Next. Now here are a bunch of options that you have to choose as per your COBOL code. I am just choosing few and I will just keep rest of it as default. Encoding I am giving as CP037 and then I'm going to click on Next. I'm just clicking Next. Now here you can see that there are different options which are available, which you can use based on the type of database that you want to use for your backend. Now here there are three different options: Postgres, MS SQL, and DB2. I'm just leaving it as Postgres here. Click on Next and then Finish. Now here this has created a template for our code. Now in order to do the transformation, what I'm going to do is I'm going to right click and then go to Blue Edge Velocity and then say Modernize from Analyzer DSLs. I'm going to select the license from Blue Edge. I am going to give it a name and then give my package a name. I am giving my package name here com.netfactor.aws. You can give it any name that you like and then press OK. Now here you can see that it is now transforming all our code. Now while it is doing the transformation, what I'm going to do is I have already transformed the code in another screen, which I'm going to show you how the transform code looks like. So here I go into service. And here you can see all our code has now been transformed into Java, Spring Boot. And you can see that all our front-end code in the web layer has now been transformed into Angular application. Now, in order to deploy this code, what I'm going to do is I'm going to deploy it in a Tomcat server, which I'm going to start. And all my front-end code, I'm going to deploy it into an NPM server. So let's go ahead and start that as well. So our servers are starting now. Let's go ahead and look if our Tomcat server has already started. Our server has started now. So let's look at our Angular screens. type here menu, enter, and here you can see that our Angular screen is looking similar to how our CICS screen used to look. So in this case, we don't have to train our end users. They will be using the same familiar screens. You can also customize this screen according to your organization standards with like HTML style sheets, or modernize it further with drop downs or a modern style. Now, in order to display customer information here, I'm pressing 1, pressing enter, and I give my customer number. Press enter, and here you can see the name and address of the customer is displayed. I would also like to show you how I migrated my vSAM files to database. In order to do that, I connected to BlueXAM tool, and then I gave the path to my listcat folder. This is the place where I showed you a bunch of JSON files in the analyzer tool. Then I clicked on load. As I clicked on load, it created all the schemas for my table into my Aurora Postgres database. I have connected my Aurora Postgres database using the pgadmin tool. Here you can see it has created a bunch of tables for me. Now let's just look at how many rows are there in the invoice table. Go and count the rows. So the number of rows here is right now 11. Let's just go ahead and enter an order. Giving my customer number, product code, quantity, and press enter. Here you can see the order has been posted. Let's go ahead and look at the number of rows if it has been updated. Now here you can see the number of rows has been updated to 12. Now as the code is refactored, you will be able to make use of all the cloud native capabilities. Thanks for being with us today, and now I will hand it over back to Madhuri.
Thank you, Kirti. Automated refactoring tools now bring in further agility by supporting serverless. Using serverless, not only is the monolith broken down into separate services, but the services become smaller functions with no need to manage servers or containers. With AWS Lambda, there's no charge when the code is not running, so this can further reduce the cost. Serverless can enable customers use polyglot architectures, where dev teams would like the flexibility to decide on the most suitable programming language for each service. For example, some customers employ large teams of COBOL developers that they would like to retain, whereas others suffer from mainframe skill gaps, so they would like to switch to more popular languages quickly. Customers also require agility in transitioning to cloud. This means they have to run part in the cloud and part in the old. Polyglot architectures facilitate flexibility in transitioning as well. So this chart gives a table of mapping between the source stack, the target stack, and the AWS services that can be used for each component. Remember that the supported languages, the supported data formats, or even the JCL and the transaction systems supported, all of this varies among the different refactoring tools. So what is shown here is more of a guidance on the most commonly used mainframe technology according to us, but this certainly is not a union of all of them. For example, there are refactoring tools such as Anubex that can convert assembler to Java, but that's not listed here. And these are some references for you to look up. And with that, I would like to open up for Q&A. Thank you.